All right, welcome everyone. This is your ultimate rapid-fire revision guide for light, reflection, and refraction. One of the most important chapters for your board exams. Let's make sure you absolutely nail it.
So let's start with a really simple puzzle, something you've probably seen 1,000 times in your kitchen. It's right out of Activity 9.1 in your textbook. You look at one side of a spoon, you're tiny and right side up, you flip it over and suddenly you're huge and upside down. So, what's going on there?
Well, it's not magic, it's just physics. And in the next few minutes, we're going to break it all down. From reflection to refraction, all the mirrors, lenses, and formulas, everything you need to turn these concepts into serious marks on your exam.
First up, reflection. You know, the whole reason we can see anything is because light bounces off stuff and into our eyes. But here's the thing, it doesn't just bounce randomly. Oh no, there are rules.
And here they are, the two unbreakable laws of reflection. Law number 1, the angle the light comes in at, that's the angle of incidence, is always equal to the angle it bounces out at, always. And number 2, the incoming ray, the reflected ray, and the normal, which by the way, is just a fancy name for an imaginary line you draw straight out from the surface, they all lie on the same flat plane. These two rules, they explain every single reflection you'll ever see.
Okay, so we've got flat mirrors down. Now let's move on to the really interesting stuff. The curved ones, like our spoon. These are called spherical mirrors, and they can completely change the way you see things.
And the difference is all in the curve. Think of it this way. Concave mirrors curve inwards, like you're looking into a cave. They cause light rays to converge or come together. On the other hand, convex mirrors bulge outwards, and they do the opposite. They make light rays diverge or spread out.
Okay, this next bit is absolutely crucial for your exam. The difference between real and virtual images. A real image is formed where light rays physically cross paths. You can actually project it onto a screen, just like in a movie theater, and it's always inverted. Yep, upside down. But a virtual image, that's where the rays only look like they're meeting behind the mirror. You can't project it, and it's always erect, or upright.
Now this table, this is basically your secret weapon for concave mirrors. It's a summary of Table 9.1 from your textbook, and it shows you every single possible image you can get just by moving an object around. The big takeaway here is that concave mirrors can do it all. They can form both real and virtual images. Seriously, memorize this table, it's guaranteed marks. And hey, this isn't just some abstract theory. We use this stuff every day. Think about car headlights or torches. They use concave mirrors to focus light into a super powerful beam. And that side view mirror on a car that says objects in mirror are closer than they appear, that's a convex mirror. It gives the driver a much wider view of the road.
Okay, so we've totally mastered what happens when light bounces off something. But what happens when light goes right through it? This brings us to the next massive idea, refraction. I mean, you've all seen this happen, right? You stick a pencil in a glass of water and it looks like it's broken. This classic illusion is the perfect example of refraction in action. The light coming from the pencil actually changes direction when it leaves the water and enters the air, tricking your eyes into seeing a bend.
So why does it bend? Well, it's all about speed. Light travels at different speeds through different materials, or mediums. When light goes from a rarer medium, like air, into a denser one, like water, it slows down and bends towards the normal. And when it goes the other way, from denser to rarer, it speeds up and bends away from the normal. Simple as that.
And just like reflection, refraction has its own set of unbreakable laws. The first one's going to sound familiar. The incident ray, the refracted ray, and the normal all lie on the same plane. The second one is the famous Snell's law. It's just a mathematical way of proving that the way light bends is totally predictable. That ratio it talks about, we just call it the refractive index.
So, how can we use this bending of light to our advantage? Well, that's where lenses come in. A lens is just a carefully shaped piece of glass designed to control exactly how light refracts when it passes through. And you'll see a pattern here, just like with the mirrors. A convex lens, which is thicker in the middle, converges parallel light rays to a single point. You know, like a magnifying glass. A concave lens, which is thinner in the middle, does the exact opposite. It diverges the light rays, making them spread out.
And here we go again, another golden ticket for your revision. This is a summary of Table 9.4. And notice the parallel with concave mirrors. The convex lens is also the all-rounder, able to form both real and virtual images. This is an absolute must-know for your exam, guys.
All right, deep breath. Let's tackle the part that I know can be a bit scary, the math. But trust me, we're going to make the sign convention and formulas super simple. Getting this right is the key to solving all those numerical problems.
Okay, forget all the complicated rules. Just think of it like a simple graph from your math class. The pole of the mirror, or the optical center of the lens, that's your origin, 0, 0. The object is always on the left. Anything to the right is positive, anything to the left is negative. Anything up is positive, anything down is negative. That's it. Seriously, follow that and you can't go wrong. And here it is, the mirror formula. It's a beautiful, simple relationship between the object distance u, the image distance v, and the focal length f. Just remember to plug in your numbers using those sign rules we just talked about.
And now, look at the lens formula. Look really closely. Do you see it? The only thing that changed is one little sign, a minus instead of a plus. It's a tiny detail, but it changes everything in your calculations. Please, don't mix these two up.
Finally, what's all this talk about the power of a lens? It's just a way to measure how good it is at bending light. You just calculate the reciprocal of its focal length in meters, and the unit is the diopter. That D on your glasses prescription? Yep, that stands for diopter. Positive power means a converging convex lens. Negative power means a diverging concave lens.
Okay, let's lock all this in. Rapid fire summary time. You ready? Mirrors reflect, lenses refract. Which ones are the versatile all-rounders that can do it all? That's the concave mirror and the convex lens. They can form both real and virtual images. And which ones are the predictable specialists? That's the convex mirror and the concave lens. They always give you a virtual, erect image.
See? You've got this. You've covered the core concepts, the key tables, and the essential formulas. You are prepared. Walk into that exam hall with confidence, knowing you understand how light works.
And I'll leave you with this one last thought. Mirrors reflect the world to you, and lenses refract light so you can see it. But did you know your own eye has a tiny convex lens inside? The very physics we just crushed is happening in your head right now, letting you watch this. Makes you think, right? Good luck with your exams. You're going to do great.